All right, let's get right into it. You turn on the tap every single day, and you just trust that the water coming out is clean, it's safe. But behind that simple act, there's this whole hidden drama playing out, a chemical story that's all about keeping us healthy. And it turns out the hero of that story, it's got a pretty big secret.
So, the hero I'm talking about is disinfection. It's the absolute foundation of modern water treatment. It's our shield, right? It protects us from all sorts of nasty pathogens. We're talking bacteria, viruses, you name it, that are just hanging out in our rivers and lakes. Things like chlorination, they're the unsung heroes of public health. They've saved countless lives, no question about it. But here's where it gets interesting, where the plot really thickens. What if that exact process, the one that's designed to keep us safe from one thing, actually ends up creating a totally different kind of threat? What if our chemical shield has a side effect, a hidden consequence that we're only now really starting to grasp? To figure this out, we've got to introduce another character into our story. It's a secret ingredient, really. It's hiding in plain sight in all of our water, and it's called natural organic matter. So what on earth is natural organic matter, or NOM for short? Well, it's pretty much exactly what it sounds like. It's this complex soup of organic stuff from decaying leaves, plants, soil. You get the picture. I really love this analogy here. Think of it like nature steeping a giant pot of tea in our rivers and lakes. It's literally everywhere, in every single natural water source on the planet. Now, this NOM has some interesting characteristics. Depending on the local rocks and the weather, it can change how water looks or tastes. It can even act like a little taxi, carrying other pollutants around with it. But here's the absolute key takeaway. On its own, NOM isn't a direct threat to us. It's just a normal, harmless part of the ecosystem. The problem starts when we try to clean the water. Okay, so we've got our hero, disinfection, and we've got this seemingly innocent background character, NOM. The trouble kicks off when these two finally meet. This is where that unwanted reaction happens. And the process is actually pretty straightforward. First, you've got your regular source water, which, as we know, is full of NOM. Second, you add a powerful disinfectant, like chlorine, to kill all the germs. But here's the thing. That chlorine is a really strong chemical, and it doesn't just go after the pathogens. It also attacks the NOM, breaking it apart and creating a whole bunch of brand new compounds. We call these disinfection byproducts, or DBPs. And this is where the scale of the problem just becomes mind-boggling. We're not talking about one or two new chemicals here. No, scientists have identified more than 700 different kinds of these DBPs in our drinking water. Just let that sink in. Over 700 unintended chemicals being created in the very process meant to make our water safe. Okay, so we've accidentally made hundreds of new chemicals. The big question is, does it matter? Are they actually dangerous? Well, the answer to that is precisely why DBPs have become such a huge concern for scientists and health officials around the world. This table, which comes straight from the source material, really spells it out. The most famous group, the trihalomethanes, includes things like chloroform, and yep, they've been flagged as carcinogenic. But check out the others. You see words like cytotoxic and genotoxic. All that means is they can be toxic to our cells and could even damage our DNA. The research is really starting to connect long-term exposure to some of these DBPs with serious health problems. And get this, not all DBPs are created equal. Not even close. Their toxicity can be wildly different depending on what they're made of. As you can see here, the ones that have iodine in them tend to be the worst of the bunch. The ones with bromine are somewhere in the middle. And the DBPs made with just chlorine are usually way less toxic. This is super important for figuring out how to manage the risk. So here's the thing. This is all still an active area of scientific research. Trying to study and regulate over 700 different chemicals is a massive job. A lot of them are still unregulated simply because we don't have enough data yet. But as we learn more about what they do to our bodies, you can bet the rules for what's considered safe in our water are going to keep changing. So how in the world do you solve a problem like this? You can't just stop disinfecting the water. That's a non-starter. The risk from pathogens is way too high. No, the smart solution is to get ahead of the problem. It's about winning this chemical battle before it even has a chance to start. And this quote from the literature just nails it. The reaction needs two things, a disinfectant and NOM. So if you want to stop the reaction, you just have to take one of those things away. We absolutely need the disinfectant, so the target has to be the NOM. If you can get most of that natural organic matter out of the water before you add the chlorine, you can slash the amount of DBPs that get formed. So how do you get rid of NOM? It's a really clever process called coagulation, flocculation. Here's how it works. First, you add chemicals called coagulants. These neutralize the electrical charge on all the tiny particles. Then, you gently stir the water. This makes the neutralized particles start sticking together, forming bigger and bigger clumps called flocks. And finally, you just let it sit. The flocks get so heavy that they sink right to the bottom, taking all that with them. It's a pretty elegant way to solve the problem. But, of course, that's not the end of the story. The science of keeping our water clean is always changing, because the challenges are always changing too. So let's wrap up by looking at what's next, the problems we're still facing, and the incredible innovations that might just save the day. Now, this process isn't perfect. It creates a lot of sludge you have to get rid of, and it doesn't work so well when the water is really cold. But there's a new bad guy entering the story: climate change. It's actually changing the very nature of the NOM in our water, which is making it a lot harder to remove with our traditional methods. But this is where it gets really, really cool. Scientists are working on a whole new generation of solutions. We're talking about more efficient metals like zirconium. We're talking about nanotechnology, using things like tiny carbon nanotubes to pull NOM right out of the water. And maybe the most exciting of all, they're looking at natural solutions, stuff like chitin sand from crab shells or proteins from the seeds of the moringa tree. These could be total game changers: sustainable, biodegradable, the whole package. And that leaves us with this one final, really important question. The mission to provide water that's both safe from germs and clean of these chemical byproducts, it's a constant balancing act. As our world changes, our water changes with it. So the real challenge isn't just about what we're doing today. It's about how we're going to keep innovating, to keep protecting our most vital resource, and to make sure that the water from every tap is truly, completely, both safe and clean.